Hello everyone and welcome to my channel From Root to Best. Today we will talk about a very interesting problem, that is counting number of set bits till a given integer n. What exactly does that mean is, so we will have a integer value n, for example 7. Now starting from 1 up to 7, we have to check how many set bits are present in every number, and then we have to find total number of set bits. A set bit means in the binary representation of that integers, how many ones are present. So for example, as I said, let's say our number is 7. Okay, so n's value is equals to 7. Now, as I said, starting from 1 till n, we have to check for every number that how many set bits or how many ones are there in their binary representation. Starting from 1, if we talk about 1, so 1 is represented in binary, we represent 1 as 1. So total number of set bits we have 1 only. Okay, 2, right? So 2 we represent as 1, 0. Number of set bits 1 again, correct? Then 3 represented as 1, 1. Number of set bits we have 2. Then 4 represent as 1, 0, 0. Number of set bits 1. Similarly 5 it will be 1, 0, 1. Number of set bits we have 2. Then 6 it's 1, 1, 0. Number of set bits again 2. Finally 7. 7. Binary representation of 7 is 1, 1, 1, right? And total number of set bits is 3. Okay, so now our expectation is the sum of all these numbers. So all these numbers are the number of set bits present in their respective binary form, and we will have to return total of this number of ones. Okay, so we have 12. So this is our expectation. So if we give n as 7, we should get output as 12, because starting from 1 till 7 in their respective binary forms, if we count the total ones, it will be 12. Okay. Now what's our solution? Now it's quite clear that we have to iterate from 1 till n. We have to find their bit set count and then add it in the total. Now to find the bit set count, what we can do, we can simply check whether the first bit is 1 or not, that is LSB. If we can set as LSB, the first bit, right? So we will check whether the first bit is 1 or not. If it's 1, we will add it in the count. If it's not, we will use a shift operation so that the next bit can come to the LSB will be, the entire bit will be shifted 1 bit right. So the next bit will come in the LSB position. Okay. So for example, if we perform right shift, 1-bit right shift operation on 2, so 1 will come at LSB and 0 will be lost. Then again we will check whether that LSB is 1 or 0. So we will keep on shifting the entire number 1 bit right till the number is becoming 0. Okay, so that's our straightforward approach. How we will write that solution? Let's say we will have int, for example, just I'm assigning it with 7. You can have any number, any integer number, right? And we have a total, okay, initialized with 0. Now we will iterate, yeah, starting from 1, where I less than equals to n, I plus plus. Okay, here we will just assign the I in a variable num, because we will perform shift operations on that number. So if we directly modify n, the entire loop will get affected, right? So that's why we will use a new variable. Now what I said, we will keep on shifting the entire number 1 bit right until and unless the number itself is becoming 0, right? So while num greater than 0, okay, what we will do, we will simply check whether the LSB is 1 or not. Now how we will check whether LSB is 1 or not? One way to check whether the decimal form of that number is even or odd, because when the decimal form is even, the LSB will always be 0, and when the decimal form is odd, the LSB is always 1. So that is one option. So we can simply write here total plus equals to num modulo 2, right? So if its modulo, I mean remainder is 1, that means it's an odd number, so we will add 1 in that total. And if it remainder is 0, that means it's a even number, and we will add 0 in the total. Okay. Or we can have a if else check here, right? This way also you can do. So let me just write that way for your understanding. If equals to 1, then only we will update total, okay, else not. And next we will shift the entire number 1 bit right, right? So num equals to num right shift 1. Okay, so this is our straightforward solution. This solution, what we are doing, we are simply checking all the digits starting from 1 to n, and then we are checking whether the LSB is 0 or 1. If it's 1, we are adding it in our total, and then we are shifting the entire number in 1 bit right. So also you can this solution in another way. Okay, let me show you that way also. Instead of modulo, so here in all the binary representations, perform an AND operation between number and 1. So 1 will always have only 1 in the LSB. Now if we perform AND operation, so if the LSB of that number is 0, the result will be 0. And if the LSB is 1, the result will be 1, right? So instead of checking this modulo operator, what we can check, we can simply perform AND operation, okay, and sorry, not AND operator, we need to use bitwise AND operations, and we can check this. So if number and 1 is 1, that means the LSB is 1. So we will increment the total, and else we will skip and we will simply use shift operation. Okay. This one we can also use this way. Instead of shifting using shift operator, if you want, you can use this. Why this will work? Because see, when we are shifting the entire digits one bit right, so what we are losing? We are losing a power of 2. Correct? So power of 2 losing means we are actually dividing the entire number by 2. Okay. So for example, this, let's say 5. So 101. So it's 2 to the power 0, 2 to the power 1, 2 to the power 2. Now when we shift, it will remain 2 to the power 0 and 2 to the power 1. Then for one more shift, 2 to the power 0. So every time we are simply losing a power of 2. That means we are actually dividing the entire integer in half, or we are dividing it by 2, right? So that's why this will also work. Okay. So for your understanding, since we are using modulo here, let me change this to the normal arithmetic operations divided by 2, and here let me have it the shift operation, because here we are using bitwise operation at the top, right, in the inside if condition. That's why shift operation. So both the logic is same. I mean, we are not doing anything new or anything additional. Both the solutions are exactly same, except here we are using normal mathematical operations like modulo operations, then division operation, and here we are using bitwise operations. So bitwise and bitwise shift operation. Okay. In both the solution, if you check, what will be the time complexity? Time complexity. What will be the time complexity? So we have nested for loops. First for loop, we are iterating till n. So it will iterate n times. Okay. So it has to be first n. Then the internal or nested while loop, every time we are actually dividing the number by 2, right? Whether we are using the shift operation or we are using the normal division operation, both the cases the number will get divided by 2. So the number will be reduced by half. So when the number is getting reduced by half, so complexity is becoming log n, right? So the final complexity of the entire solution will be n log n. Let me add approach 1. This one will be approach 2. Okay. Nothing is different. Both the solutions are same. Just the operations we are using is the difference. Right? And time complexity of both the solutions is order of n log n. Okay. Now it might look a better approach or a good approach, but it's actually not, because n log n, that means if we consider a large numbers like 10 to the power 9, or the execution time will be very huge. Then how we should find the best solution? So to find the best solution, we have to find the pattern, right? If you have followed me in my previous videos, I have always mentioned that in order to find the best solution, we first have to identify what's the pattern of the solution. Now let me write the binary forms again. Here, if you can see that at every position, okay, be it 0 position, 1 position, or 2 position, that means 2 to the power 0, 2 to the power 1, or 2 to the power 2. At every bit position, we have exact same number of set bits. So 2 to the power 0 position, we have 1, 2, 3, 4. 4 number of set bits. Similarly, 1 position, we have 1, 2, 3, 4. And on 2 position, we have 1, 2, 3, 4. So can we say that number of set bits at every position of their respective binary form will be same? So it's always be, so if we can represent the number in 3 bits, okay, so here we have n equals to 7. To represent any digits starting from 1 to 7, we need 3 bits in binary, right? So if we can represent the number in 3 bits, the number of set bits at every position is equals to 4. Let us check whether this same property holds true for any other number. Okay, so for example, say n equals to 7. If we have n equals to 15, then so here also, when we need 4 digits to represent the number, now if we can count the number of set bits at every position, you can find, so let's say first position, we have 1, 2, 3, 4, 5, 6, 7, 8. On the second position, 1, 2, 3, 4, 5, 6, 7, 8. Third position, 1, 2, 3, 4, 5, 6, 7, 8. And on the last, the MSB position, we have 8 once again. What we can observe here, that the number of set bits for every integer till n at every position is exactly same. So can we derive a formula from here, so that instead of checking each and every digit, we can simply check that what's minimum number of bits required to represent numbers, and then we can directly use the number of bits to get the total count of set bits. Let's say number of bits we are representing using k. K is equals to, this is our assumption. So when k is equals to 3, count of set bits at every bit position is equals to 4. Similarly, when the k is equals to 4, that is where n equals to 15, right? Then the count bit at every position is 8, correct? So can we say that this value is actually equals to 2 to the power k minus 1? I mean, this 4 is 2 to the power 2, 8 is 2 to the power 3. So when k is 3, output is 2 to the power 4. When k is 4, this is 2 to the power 3. So actually 2 to the power k minus 1. So finally, we can say that count of set bits at every bit position is 2 to the power k minus 1. This will give me the number of set bits or count of set bits at every bit position, right? This 2 to the power k minus 1. Now we have to multiply it with k, I mean number of bit positions, to get the total count of set bits. So final formula will be total count of set bits is equals to k multiplied by k minus 1, right? So let us try applying this formula. Okay, so in our both examples where n is 7, we need 3 bits to represent all the integers up to 7. So k's value is 3. A equals to 7. So k is becoming 3. Total count of set bits k into 2 to the power k minus 1. 3 into 2 to the power 3 minus 1. It will be 3 into 2 square, that is 4, and finally our output will be 12. So when n is equals to 15, the k will be 4 because we need 4 bits to represent the integers in binary form. Here k's value will be 4. Similarly, the formula will be 2 to the power 4 minus 1, and it will become 4. 2 to the power 3 is equals to 8, and we will have answer as 32. We can verify here. So we have 4 ones here, 4, then 4 plus 4, 8, and 4, 12, right? We have already calculated that. For 15 also we can check, and the value will be 32. I hope till now it makes sense. This formula derivation, I mean how we achieve to this position, how we find the pattern is clear to you, right? Now we have a problem with this formula. Now this, if you can see, this n value 7 or n's value 15, they all belongs to a special category. 7 is the maximum number we can represent using 3 bits. Similarly, 15 maximum number we can represent using 4 bits. Similarly, if we take 31, 31 is the maximum number we can represent using 5 bits. So this formula, whatever we have, is applicable with these special numbers only. The moment number will change, I mean it will not be that special number. So for example, n equals to 6 or n equals to 13. In both the cases, if you can see, so let me copy this. Now let's say n equals to 6. So we will represent all the integers starting from 1 to 6, or n equals to, let's say, 13. So here also this. Now if you count the set bits at every position, every bit position, the number of set bits are not equal. So here the first position, LSB position, we have 4 set bits. In the second position we have 3 set bits. On third position also we have 3 set bits. So number of set bits are not equal across different bit positions. Similarly, in this case, when n equals to 13, the number of set bits at first position is 1, 2, 3, 4, 5, 6, 7. On the second position it's 1, 2, 3, 4, 5, 6. On the third position 1, 2, 3, 4, 5, 6. On the last position or MSB position we have 1, 2, 3, 4, 5, 6 again. Now as you can see, there is some inconsistency in the number of set bits at every bit position. So we cannot apply this formula directly there. So what can we do? Right? This is just a catch. We directly when we directly apply this formula, this edge conditions, or this is one condition which will break. Now how to solve this problem? Clearly, if you can see, we can apply this formula only when n's value is a special number, which is the highest number we can denote by k number of bits, where n equals to 7 or n equals to 15. So if we can break this number into groups means a group where first group will become the numbers till that position where it will be the maximum integer represented by k amount of bits. Till that integer, we can directly apply this formula and get the total number of set bits. And for the other half or other part of that integer, we will try to find the different solutions. So for example, let me add a divider here. This one, okay. So what I'm saying, this 3, if we consider 2 bits, so 3 is the maximum integer that can be represented by 2 bits, right? Where k equals to 2. Similarly, 7 is the number which is the maximum number can be represented by 3 bits where k equals to 3. So we will break this entire series of numbers into 2 groups. One till that number where it will be the maximum number represented by k amount of bits, and for rest of the numbers we will find a different approach. So we have to find a number of bits that's required to represent this number. So here let's say n bit. Now to represent 6 we need how many bits? We need 3 bits, right? Similarly, to represent 13 we need 4 bits. So here n bit will be n bit equals to 4. Now we will break the entire integers numbers in 2 groups, where we will take first group up to n bit minus 1 bits. So if n bit is 3, we will only take k equals to 2. So where k is 2, that means the maximum number represented by 2 bits. N bit equals to 4, then we will take k equals to 3. So the maximum number is represented by 3 bits. Okay. So n bits equals to 3. So we will update k equals to n bit minus 1 minus 1. Similarly, here also k will become n bit minus 1. Okay. So here the k will be 2 and here the k will be 3. Till now it is clear. Where k equals to 2, so maximum integers represented by 2 is 3. Where k is 3, maximum integer value we can represent is 7. So till 3 and till 7 we can directly apply this formula. Okay. So what will happen here? Yeah. So n is equals to 6. So n bit or max bit we can say. Let me just change from n bit, let me change it to max bit. Okay. So max bit is 3. So k is max bit minus 1 is equals to 2. So up to 3. Total number of set bits up to 3 is k into 2 to the power k minus 1. K is 2. So this will become 2 into 2 to the power 2 minus 1. Right? Now which will eventually become 2 into 2, that is 4, right? So up to 3 we got the total number of count bits, that is 4. 1 2 3 4. Same will be applicable here also. When n's value is 13, so max bit is equals to 4 and k will be max bit minus 1, that is 3. Total number of count bits up to 7 will be k to the power k into 2 to the power k minus 1. K is 3. So the formula will become 3 into 2 to the power 3 minus 1, that will eventually result in 3 into 2 to the power 4, that is 12. Okay, so here up to 7 we got the total number of total count of set bits. Clear? This is part 1 of the solution. What is part 2? Part 2 is finding the total count of set bits for remaining numbers, right? So here 4, 5, 6, or in this case 8, 9, 10, 11, 12, 13. We have to count the number of set bits till that. Okay. Part 1 was focused till this position, right? Part 2 will focus the remaining positions. Here you can see for part 2 the MSB will always 1 because the number of bits, that max bit is 4. So we have already considered all the integers till max bit minus 1. So that means MSB for up to that position will always 0. Now the moment we comes to this next part, the MSB will always 1. So we can clearly count the total number of ones or total number of set bits at MSB position, which will be equals to the remaining numbers in that range, right? So in this case 3, in this case 6. I hope it's making sense, right? So MSB will always be 1 for the numbers which will belongs to max bit, because the other half where MSB was 0 we have already considered in the first part, right? So in the second part the MSB will always be 1 and it will be the number of 1 equal to the number of remaining digits in that group, right? So what's the number of digits remain, right? Numbers we have already covered. We have already covered 2 to the power k numbers, right? Sorry, not 2 to the power k, 2 to the power k minus 1. So here 2 bits, k's value was 2, right? So 2 to the power k is 4 and minus 1, that is 3 digits we have covered. Similarly here k is 3, 2 to the power k is 8, right? And 8 minus 1 we have already covered up to 7. So first part number of digits were, so 2 to the power k minus 1, right? Now, so what will be the remaining digits? Remaining digits will be n minus, yeah. So what will be the remaining number of digits, right? So it will be n minus this 2 to the power k minus 1, correct? Because 2 to the power k minus 1 we have covered. We had total n number of digits. So n minus 2 to the power k minus 1, right? So remaining integers or digits will be equals to n minus 2 to the power k minus 1, right? That we can further evaluate as n minus 2 to the power k plus 1, correct? So this is our formula to find the remaining digits, and the number of set bits at MSB will be same as remaining digits. So this is actually is the number of set bits at MSB position for the remaining numbers. Yeah, I hope this also is making sense. So in the second part, we actually find out what are the remaining numbers we have, and that count is actually equals to the number of set bits at MSB position, right? So now, since we have the count of MSB positions, right? So this position we have already covered. Uh, Correct. Now, if we remove, since we already got the MSB position, if we remove the MSB, what it will become? It will again become the not exactly same, but the same numbers present in the first part, right? So here, if we remove the first MSB, the numbers will become 0, 1, 2. So it belongs to the first group where it's starting from 0. So we can ignore 0 because 0 will not have any more set bits. So 1, 2, we will again it will become part of first group. Similarly, 0 we will ignore. So 1, 2, 3, 4, 5, which is again belongs to the first group. Not totally, but subgroup of the first part. Is it clear? So we can again apply the same process, right? Same process of finding count for part 1 and part 2 in the remaining numbers. So for remaining numbers, we don't have to perform any additional task. We can perform exactly same task what we did for part 1, right? Or the number. It's just the value of n will be changed. So value of n will become 2 in this case, and in this case value of n will become 5. Is it making sense? We have already got the count of MSBs, so we don't need to count it again. We are removing it, so the remaining digits are becoming a new n because it's again falling into first part. Same here. The remaining digits 1, 2, 3, 4, 5 is again becoming new n and falling into first part. So now the part 3, if I can say so, yeah. So part 3 will be finding the value of new n, right? So part 3 will be finding the value of the new n, right? So what will be the value of new n? So as you can see, when we have 3 digits remain, we are only ignoring 0, so 3 minus 1. When we have 5 digits remaining, we are ignoring 0 again, so we have, sorry, here we had 6 digits remaining, we are ignoring 0 again, so 6 minus 1, 5. So here we can clearly say that new n is actually equals to the count of MSB set weights in second part minus 1. Correct? And once we get the new n, we will follow the same process once again. Is it making sense? So, if this theory is clear, now let me show you the code for this approach where we will use recursion, because since we are again finding a new n and again following the same process, so we will use recursion to write the code for this solution. Okay, so here we will write the solution, the best solution which we just find. Okay, so just be with me. Now I will just have this method count set weight static method, because I will call it from static main method. Now since I will use recursion, first of all, the first thing I will write in this inside this method is the base condition. Now base condition will be when n is 0. The moment n becomes 0, we can simply return 0 or return n, right? Anything. Let me return 0 with a hardcode value. Now the first thing we have to do is we have to find the k is the number of bits required, or let's max bit only. Max bit is the number of bits required to represent n in the binary form. If we find n, then we can find k as well. So let me write. So basically my function will directly return k. I will show you how. So I'm just writing it as k. Okay. Max bits, not max, find max bit, right? Not max, sorry, min bits, right? Minimum number of bits. And okay. So let me write a private method, private static int min n bits in n. Now what we will do here, we will keep on checking, increasing the power of 2 and check whether that power of 2 value is greater than n or not. The moment it becomes greater than or equals to n, that's our max bit, right? Max number of bit required. And we will return 1 less than that. That's why I write it as k. I wrote it as k because we will automatically return 1 minus of that minimum bits. Okay. So let me just have n, let's say max bits is equals to 0, right? Initially it will be 0. Now I will keep on checking, it will be power, right? So to find the power, I can directly use methods or use inbuilt functions, but let me write it manually here. So I will write a method to find power and I will check whether its value is less than n or not. Okay. The moment till it's less than, I will keep on doing that. I will basically keep on the number of bits by 1. The moment it becomes greater, I will break the loop and return the max bits. Okay. So I guess I have to write another private method. Int power int k. Okay. Now to find power again, I will have result equals to 1, because anything power 0 is 1, right? And I will add 4. So I will simply start from 0. I will go up to this power and then keep on increasing. I will simply multiply the result by 2, because we will find the power of 2 only here, right? For your understanding, let me just make it power of 2. Okay, because we are dealing with binary numbers, so we don't need to find power of any other value. We will always check power of 2. Okay, so we find k. Now, so first part is, right, if I first part, we can directly apply the formula. What was the formula? K into 2 to the power k minus 1. Okay, so 2 to the power k into power of 2 k minus 1. Right? Okay, let me define it. Next, so this is our first part. Second part. What was second part? Finding the remaining bits, and that will be equal to the number of set bits in the MSB position. So to find the remaining bits, let's say second part is equals to, what was the formula? N minus 2 to the power k plus 1, correct? N minus 2 to the power k, so power of 2k plus 1. And the third part is finding new value of n, and we will follow the same process, and new value of n will be second part minus 1, correct? So we can simply return the total count as first part plus second part plus calling the same method with new n, that will be second part minus 1. Right? Till now it's clear. The code is quite simple, right, and self-explanatory. Now let me write the void main method and call this function. So int n equals to, let me have 7. Set bits till n is count of set bits n. Okay, now if we run this program, so till 7 we got the count is 12, right? Similarly, if I change it to 15 and run it again, it's 32. If we change it to 13, 25. If we change it to 6, 9, right? So our solution is working fine. Okay, now I will just show you some tricks to even improve the performance of this solution furthermore. Okay, tricks is, instead of using this mathematical, normal multiplication operations to find power of 2 and finding the max bits, we can simply use bit operations that will work much faster and help us to improve the performance. This is just an additional tricks. It's not required in the during interview. During interview, if you write the entire solution this way, that's fine, that's correct. Okay, but just for adding a special effect or adding some additional performance improvement, we can use these tricks. Okay, so first of all, what we can do, instead of checking the power every time, now since we are only checking power of 2, that means we can use the shift operator. Shift operator means we can simply shift 1. Okay, let me add 1. We can left shift to max bit plus 1 and check whether it's less than n or not. Right? This is one trick we can use. Secondly, here to check the power. So instead of checking power that way, here also we can use shift operator. How? Right? Shift operator we can use so we can simply shift 1 right up to k minus 1 bits. Right? So this is one thing we can do, and it will not use any normal mathematical multiplication operations. It will use shift operator and directly find the first part, or the 2 to the power k minus 1 value. Right? Similarly, here also we can simply use okay, this one shift right shift k, right, and this one we can simply pass second part minus 1. So this code is also become less. We are not using any multiplication, we are using shift operation. Okay, now let me quickly run this program just to show you that result is still same. 6 9 7 12, then 13, 25, finally 15. It will be 32. Yeah, so this is our solution of this problem, base solution of this problem. I hope this makes sense. This helps you to understand the correct approach to find the best solution of this problem from root solution. Now, if this video helps you and you like this video, please subscribe to my channel and share this video with your friends, and also like the video. And if you want me to make any video dedicated for any specific topic, do let me know in the comment. I read all the comments and I will definitely prepare a separate video on that topic. So thanks for watching this video. We will meet again in my next video.